Right. Good morning, all of you. Welcome to this combined session, the guest lecture session. And we have a very good person with us today. Students of Brahmagupta would already know him. Sridhara batch might be a little new to Sundar. So Sundarraman is one of our earliest students, and he is right now graduating from CMI. Technically, he has finished all the exams in his college, so I'm sure he would have graduated, but he just completed his last paper now. He's very passionate about math, computer science, and computer science. So he loves to do math all the time, and that's how he has been right from school days. And we have had a lot of wonderful, opportunities to interact with him, Hariharan sir and I, um, right from the age, when he was about your age, right, Sundar, somewhere around that time, 12, 13
Yeah,
years.
1 or 2 years older. But
Yeah. So that way. Sundar, when he was in 10th standard, he started doing college level courses, especially under Dr. Rajiv Gandhi, who had taken sessions in Brahmagupta. We had done courses on discrete mathematics, and then he did a course on algorithms. And looking at how amazing he was in his classes and how dedicated he was. Just to share an example, we live in the suburban part of Mumbai, Sundar and I, and
yes,
from our place to the place where the class was conducted by Dr. Rajiv Gandhi, by train it takes about 1.5 hours. From home till the particular place. And Sundar had a class at a different place. So it was like a triangular thing that was formed. So while Sundar was attending these sessions, he would, from morning 7 o'clock till 2 o'clock, he would be attending class at a different place. And from there, he would come home, quickly have lunch, and then go to Rajiv's class, and then come back at 10:30, 10:45 at night, and then sit down to work on the assignments. And next day morning, he would continue. So this he continued for 2 weeks for every course, and that's how passionate he was. And looking at how amazingly he performed, Rajiv invited him to do a course in Princeton. So he went to Princeton about 4 years. It's been 4 years, right, Sundar?
yes, sir. 2017.
2017. So 4 years ago, in June, he went to Princeton, and he was there for about a month to do this course on randomized algorithms, and he was one of the senior students over there. And then he came back and he continued doing a lot of courses. So he's very passionate about math, very passionate about research, and he's planning to do a master's now, after his undergraduation. Uh, so yeah, so he was one of our earliest love in students, and I'm very happy that Sundar, you are here to share some ideas with all of these guys. Without taking any more time, over to you.
Thank you, sir. Thank you for such an introduction. Just a second, I'll share my screen. Yeah. So, yeah, as you can see, uh, we are going to discuss the Millennium Prize problems today. So, first of all, how many of you have heard about the Millennium Prize problems? So, you can raise your hand if you have heard of it. Okay. Anushka, Devansh, Ishan, Raghav. So, Ishan, can you tell me what the Millennium Prize problems are? Uh, I
Sorry,
cannot hear
Ishan.
you.
Yeah, not audible.
Okay, fine. Pragyan, can you tell me what the Millennium Prize problems are?
I think he took off his headset, so he's not able to
Okay,
hear.
okay. So, okay, Raghav, what are the Millennium Prize problems?
Sir, actually, I remember only two of the Millennium Prize problems. They are the P versus NP and the Riemann hypothesis.
Yeah, but what are these problems? Like what? Like, do you know why they are called the Millennium Prize problems?
I guess because they are like so left unsolved for more than so I don't know exactly.
Yeah. So that is the first question we'll address today. So we'll see what was the idea behind solving these problems, the millennial price problems, and what exactly are these problems and what is special about this. So as the name suggests, the millennium price problems were some of the most difficult problems of the millennium. So millennium is basically a collection of 1,000 years. So from 1000 AD to 2000 AD, which were the most difficult mathematical. So so there was this institute, the Clay Mathematics Institute, which is in the US. So what they did was they chose, like, on May 24, 2000, I think. Yeah, they had a committee and they chose these 7 problems. And they took the opinions of all the experts and researchers worldwide. And the main focus was that these questions should have been, like, very difficult to tackle throughout the years. So it should not have been something that was, just 5 years or 10 years old. These should be like old problems, but no one was able to solve it. So yeah, and what was the main reason? So the thing was, at this point, so in between 1950 to 2000, other applied sciences like engineering, and because of all the industrial revolution in the world war, so there was very little, like, exposure about mathematics to the entire world. So just to, make the general public aware of the things that could be done in mathematics, so these prizes were conceived. So yeah. So what exactly are these problems? So as Raghav rightly said, so the two, you could say, easiest to understand problems of these 7 problems are the P versus NP problem. So this is a computer science related problem. So this is not pure math. This is computer science and math. So if you see the Riemann hypothesis, this is purely a math problem. So you could say a number theory, or yeah, pure math. So Poincare conjecture, again, it's a pure math problem, which is related to something called topology. Hodge conjecture, again, is a pure math problem, which is related to something which is known as algebraic geometry. So you guys have learned algebra, you guys have learned geometry. So when you grow up, you will learn something which is a combination of both of them. So it's called algebraic geometry. So yeah, Hodge conjecture is related to that field in mathematics. And these two are problems which are related to physics. So these are not mathematical problems, but these are physical problems which have a lot of mathematics. And then this again is another number theory. So there is a branch called algebraic number theory. So you have learned algebra and you have learned number theory. So this uses both algebra and number theory. So yeah. So if you see, there are 3 applied math problems and there are 4 pure math problems. So this was also one of their criteria, that the number of applied math problems and the number of pure math problems should be around the same, because we needed to show the entire world, like, why mathematics was important. So only if we showed them the pure math part, they would be like, there is no application. So there were also the applied. So yeah, till here, is everyone clear, or does anyone have any question? So Anushka, yeah, you have raised your hand to ask anything. Okay, so I guess since there is no questions, yeah. So the first thing we'll look at is the P versus NP problem. So yeah, so I think the Brahmagupta batch students would know this, but does anyone from the Sridhara batch know what an algorithm is? So yeah, so Ishan, you have raised your hand. So Ishan, what do you think an algorithm is?
Yes, algorithm is a function to proceed with that to complete the task.
Okay.
Means
Tanish,
like
what?
we use algorithms in Rubik's cube. We can use it in computer, and many of them are also present in maths.
Yeah, nice, very nice. Tanish, what do you think an algorithm is?
I think an algorithm is like a process done continuously to get a certain outcome.
Okay, nice. Swasti, what about you?
I think an algorithm is so a step by we give a step by step um rule book, we can say.
Oh, yeah, so as these guys rightly said, so let's stop here. So as these guys rightly said, an algorithm is basically a step by step instruction. So this is like first step, second step, and so on. So these are like instructions given to the computer. So when you grow up, they will also call this a machine, because it can also be a lot of things. So as you know, even calculators have algorithms. So basically there will be a machine. You will have an input here. You will input something, and then the machine will follow these steps, and then you will get an output. So the collection of the collection of these steps are called the algorithm. So this is the algorithm. So yeah, so there are a lot of algorithms, and yeah. So but there is something called an efficient algorithm. So what do you mean by an efficient algorithm? So an efficient algorithm is an algorithm that solves large input in comparatively small time. So what do I mean by comparatively small time? So let's say I have an algorithm A and an algorithm B, okay, which does the same job. Let's say if you input X into the algorithm, A will give X square, and if you input X to the algorithm, B will also give you X square. But the thing is, if X is 1000, A takes 5 seconds and B takes 2 hours. So which of these two algorithms are more efficient? Yes, Srinandan. What?
Algorithm A.
Yeah, algorithm A is more efficient because this is faster. So what we have done, so what computer scientists have done, so they have taken a set of all algorithms. So basically, let's say you have an algorithm A which has some steps, let's say k steps, okay? And each step takes some time t. So the total time taken by the algorithm, each step takes time t. So the total time taken by the algorithm is kt, right? So if you look at different values of kt, so what the computer scientists have done is they have divided this into something known as efficient and non-efficient. So I won't go deep into that because it will take a lot of time. But efficient times are all which are polynomial in the size of the input. So okay, so this is a lot of words. So all of you understand what a polynomial is? If, yeah,
No.
okay. Uh, who said no? Okay, who said no?
Sriram.
Yes, yeah, Sriram. Yeah. So a polynomial is basically if you have a variable n, a polynomial is basically n square or n cube plus n, or basically anything like n power some integer plus something times n power the other integer. Sorry. Something times n power some other integer plus b times n power some other integer, and so on. Is this clear? So yeah, this is clear, right? Yeah. So if it is of this form, then the computer scientists call it an efficient algorithm. And if it is of some other form, let's say 2 power n or n factorial. Okay, and again, does everybody understand what a factorial is?
Yes, sir.
Yeah, yeah. So 2 power n, n factorial, all these are algorithms which are non-efficient. So let's take an example. So what is n here? Sorry, I forgot to say what n is here. N is basically the size of the input. So for example, if you input, let's say 1000, then n will be 1000. So, and there is a reason. So why is this efficient and why is this not efficient? So let's consider n equal to 20. And let's consider an algorithm which takes n square steps. So how many steps will this take? Yeah. Yes, Srinanda?
Steps.
Yeah, 400 steps. But let's say you have another algorithm which takes 2 power n steps. So then how many steps will this take? Yes, Siddharth?
Oh, okay. I thought I couldn't unmute. Okay, so here's the answer. The answer is 2 power n will take 2 power 20. 1048576.
Yeah. So
Yeah, but
2 power 20 is, yeah, Siddharth, you
okay.
can mute yourself.
Yeah, I want to tell something. I have a slight doubt.
Yes.
So basically, my doubt is, okay, so if n equals 20 and some algorithm takes n square units of time,
Yes.
400 units of time, but if it's 2 power 20 is way too much, right?
Yes.
Yeah, we learned something about algorithm from Rajiv sir.
Yes. Yeah. So yeah. So as Siddharth rightly said, 2 power 20 is very, very greater than 400. So that is why we say that this is a non-efficient algorithm and this is an efficient algorithm. So does everyone understand what do I mean by an efficient algorithm? Yes, I hope
Yes.
everyone understands. Oh, okay. Yes, Anushka. Hello.
Yeah, I have a doubt. By efficient algorithm, it's an algorithm that solves a large input in a comparatively less time, but it doesn't have to be like comparatively to only algorithms that perform the same thing. You can
Yeah,
compare it to
not
other.
necessary. Yeah,
Okay.
yeah. So that is why so since that is a very vague definition, computer scientists have clearly created a boundary. So if your algorithm runs in some polynomial units of time where the variable is the size of the input, then you say it's an efficient algorithm. Otherwise, you say it's not an efficient algorithm.
Okay, so the polynomial for n square is just n square. That's the
Yeah,
polynomial.
n square is the polynomial. So you can have n cube plus n as the polynomial and so on.
Yeah, but 2 power n or n factorial, they aren't polynomials.
Yes, they aren't polynomials. Exactly. Vagishan, yes?
Yes. So what if we take what if the amount of time is something like this? What if it's something like this?
You mean it takes n equals, you mean it will take like 1 square plus 2 square plus 3 square
Yeah.
plus 4 square units of time?
Or like 1 square times 2 square times 3 square.
Yeah,
Like,
but the thing is, if you take it up to
are these
infinity,
polynomials? So that's the first term.
Is it
no, but there are infinite number of terms, right? And it's a divergent series. So the time taken will be infinite.
Okay,
So clearly it's not an efficient.
Efficient, or
Yeah,
like
it will
let's
not be
say
efficient because it
let's
will.
say that sigma or pi has one finite value like 100. Then will it be a polynomial?
Yes, exactly. Then it will be a polynomial. So
Or
if you
what
have,
if and is it okay like are you it allowed to use irrational numbers or something like this?
yeah,
In
irrational
a
numbers are
poly-
okay because you can always upper bound an irrational number by a constant, right? So if you have ex, like en, sorry, not x, our variable is en, then you can always say that this is less than 3n, right? And we know that 3n is an efficient. So since it takes less time than 3n, it should also be efficient.
Okay. Or what if it's
Okay, we don't go
n
towards complex numbers because
that's true.
yeah, we don't go towards complex numbers because we are doing the computations in the real world. So the running
Yeah.
time of the algorithm will be a real.
Okay, so basically, if the algorithm is in a polynomial format, then it's a efficient algorithm. Otherwise, it's a non-efficient algorithm.
Or like what about stuff like absolute values and
Absolute value will not yield much anyway, as you are considering positive units of
Also,
time.
can you guys not like annotate because I mean, yeah.
what if we are using like sign of n or something?
Yeah, we'll look at that later. We'll look at that later.
What if that's the amount of time?
Yeah, it will still be efficient, but we'll see why it is efficient later. So the Hyderabad students, so there are not a lot of Hyderabad students, so like raising their hands. So are you all clear with this? This is because the Brahmagupta batch students had an algorithm class. So are all the Hyderabad students clear why this is an efficient algorithm and the others are not?
Yeah.
So yeah, now we'll go ahead. So what do you mean by verification of a solution? So as I had shown you, a machine, if you have a machine, you have an input and you get an output, right? So what I am interested now is to verify. So for example, let's say your professor gives you a problem and you solve it. But the thing is you are not sure about your solution. So what you will do? You'll go to the TA, you'll give him the problem, you'll give him your solution, and you'll just ask him whether my solution is right or my solution is wrong. Right. So because you don't want the TA to give you the answer, but you still want to see whether what you have done is right or not. So this is exactly what the verification algorithm does. So let's say you have a verification. So it's called a verifier. So let's say you have a verifier. So what you do is in the original algo, what you do, you take the input, you give it to the algorithm A. So you give it to the machine A, which runs the algorithm A and gives you an output. So now what you do, you have a verifier B. So you give an input to it. You give your solution to it. So you give your output to it. And it will output yes if your output is correct, and it will output no if your output is correct. So let me give you an example. So let's say, let's say given a list of numbers, let me give you a list of numbers 2, 4, 5, 7, 11, 12. And you need to find the number of primes in this list. So what that will be is you give the input in the machine M, and then it will output that there are 3 primes which are 2, 5, and 11. Sorry, 4 primes which are 2, 5, 7, and 11. But in the verifier case, what will happen is you will give the verifier 2, 4, 5, 7, 11, 12, and you will give them the answer 257, which is 3, and then the verifier will give you that your answer is wrong. So it will output no, because the answer is 4. So till here, is it clear? Yes, Anushka, what's the question? Hello. Does anyone have a question? Yes, Ishan, what's your question? Hello, am I audible? Hello.
Yes, you are.
I don't have a question. Just I forgot to lower my hand.
Okay. So yeah, is everyone clear with this concept?
Yes, I'm clear with this.
Yeah. So yeah. So now we have defined what verification is, what an efficient algorithm is, and what an algorithm. So we are all set to understand what the problem exactly is. So the problem says that the whether or not for all problems for which an algorithm can verify a given solution efficiently, an algorithm can also find that solution. So what this means is, so let me explain it. Yeah. So if you have a problem P, and you know that if you give a problem P and a solution S, there exists a verifier V, which will efficiently tell you yes or no. Yes if the problem is right, no if the problem is wrong. Then thus this implies that there exists a problem P, there exists a machine M which will efficiently give you the answer S using the algorithm A. Does everyone understand the statement of the problem? Yeah. So Tanish, can you repeat what the statement of the problem means?
So I think you asked like, um, is there a machine P which can solve the problem S correctly?
No, 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 no. So what I said was there is a problem P and there is a solution S, right? So what I'm saying is, given that you have a verifier V, which when provided with the problem and solution tells you whether it's the right solution or not, then there exists a machine M which will take algorithm A and solve your problem.
Okay.
So can you repeat it? Like, can you?
Yes. So there is a problem P and a solution S, and there is a verifier V which can give the answer yes or no. So is there a machine M which can solve the problem with an algorithm A?
Yeah, but the catch point is that A should be effective. No, A cannot be like, taking 2 to the n or anything. So it can also provide the solution efficient.
Okay, thank you.
Sir, I have a question. Vinay here.
Yes.
So, did you say there is a machine, or is the question is there a machine? Because I think
No, no.
Tanish said,
So
is there a machine? And I think I heard you saying there is a machine.
no, no. So like, is there a machine? So is there a machine with the algorithm A which can solve the problem?
Okay, okay.
So this is the question. Yeah, yeah, there is a question mark over here. So if this is true, is this true? That is what we want to know. So I hope everyone is clear with this. So I'll, yeah. So, so the class of questions for which the algorithm can provide an answer efficiently. So for example, like if you take an algorithm, so it will take in n, then what it will do, it will multiply n by 2, n is equal to 2 times n, and then it will output n. So for example, this is an algorithm which takes just constant time. So it does multiplies it by 2. So this is an efficient algorithm. So whichever question has an efficient algorithm, we call them the class P. So basically, since this question has an efficient algorithm, we say that the problem of doubling a number is in P. Does everyone get why this problem is in P? Okay. So yeah. So yeah, we know that the class of questions for which the algorithm can efficiently answer the problem is in P or just P. Yeah, class P or just P. So the class of questions for which an answer can be verified efficiently. So remember, the first condition of the problem was if there exists a verifier V. Oh, okay, so too many variables. So if there is a verifier V, is verifier V. So remember, we said that if we know that there is a verifier V such that if you input the problem and the solution, it will give you yes or no. Then, so if this, then you have a problem to algorithm to solution machine. And so basically, if this is efficient, then this is also efficient. So all problems in this category are called NP problems. So obviously there can be problems for which even the verifier is not efficient. So we will not discuss about those problems now because those are like very hard problems. So these problems are hard problems. So these problems we just know that there exists a verifier. So and these are easy problems because we actually know the algorithm. So this the computer can actually do. This the computer can actually only verify. So we want to bridge this gap. So we want to say whether they are equal or not. So is everyone clear what the problem means? Yeah, I guess everyone is clear. So yeah. So most mathematicians and computer scientists believe that P is not equal to NP. And what do I mean by P is not equal to NP? P was the problems of this kind. You have a P, you have an M, you have an algorithm A with machine M, and then you have a solution. And then you have a P and an S and a verifier and a yes and no. So most people believe that these two categories are not equal. Okay, now can someone tell me if a problem is in P? So if you know there is such an algorithm, can you find the verifier which is also efficient? Yes, Tanish.
For some problems, it is easy to do, but for others, it may be hard to do.
Yeah, so you're saying for some problems, if there is an algorithm, you can easily find a verifier, but for other
Yes.
problems, it's not possible. Okay.
So if
Sai,
it's like 2 to the power 10 to the power 800, then we can solve it, but then there's no like good verifier to check if they're correct.
Yeah. Okay. So what I'm saying is this algorithm, is efficient. So if you have an efficient algorithm, can you have an efficient verifier?
Oh, I think then yes.
Yeah, then yes. So yeah, very good. So that was, yeah. So Srinandan, what do you think?
I think yes, because if there's an efficient algorithm and once you finish it, you can just reverse the algorithm and put it in the verifier.
Exactly. So Sai, you were saying no. So why do you think it's not true, Sai?
Yes, sir. I actually think that it will take one or it will take we'll have to use the even if there is one efficient algorithm, the verifier will only be efficient among other verifiers.
But that is what we defined efficient, right? I mean, so we said that if it is if it is not exponential, then it is uh, efficient. Like if it is polynomial, then it is efficient. So yeah. So
I
Then I agree.
yeah. So as
I
Srinandan,
might have accidentally just.
want to tell something.
yes, Siddharth, yes. What do you want to say?
Okay, but okay, so if you have an algorithm that has a problem P and outputs S, obviously there will be an, and if the A is efficient, then obviously there will be an efficient verifier.
Okay, how?
Because the verifier can use the algorithm A to check if it's right or not.
Exactly. So as Siddharth, Sai, Tanesh, and Srinandan are saying, so what the verifier will do is it will take the problem P, take the solution S, and inside the verifier P, what it will do is this is the verifier. So it will run P through A and get an S prime. And then what it will do, if S is equal to S prime, it will output yes, else it will output no. And since we know that this algorithm is efficient by our assumption, we know that this verifier is also efficient. So yeah, so let me clear all my points. So basically what we know is, we know that some problem P, some problem, let's
Yeah, so
say, yeah,
basically P implies
yeah,
NP.
yeah, P belongs to P implies the problem P belongs to NP.
Yeah.
This we already know. So
Yeah, but what we need to find out is if we have a verifier, will there be a algorithm that works efficiently?
exactly. So our question is this: if you have a problem which belongs to NP, does this imply that the problem belongs to P? Yeah. So the thing is, now you guys don't have information about complexity analysis and running time analysis and so on. So we will not see how exactly people have tried to solve this, but we'll just, yeah, this is just an introduction to the problem, because remember, these are the hardest problems of the century. So even understanding these problems is a sort of a not so easy task. So yeah, that is the whole point of this session. Yeah. So Tanish, yes, what happened?
How can we have like a verifier if we like don't have any algorithm to solve the problem?
Oh, very good question. Yeah. So consider this example. So let's say you have a graph. So does everyone know what a graph is? So if anyone who doesn't know what a graph is, please raise your hand so that I can explain. Okay.
I'm not sure if they are thinking of X and Y axis.
Oh, okay. Okay. Let me define the graph. So you have certain points. So these points are called vertices. and you have lines between them. So that is this one. So these lines are called edges. So a graph is basically a collection of some vertices or some edges. So is this clear? Is this definition of a graph clear?
Yes, sir.
Yeah. So yeah. So given a graph,
Graph with points and edges, right?
yeah. Yeah. So if you have a graph with vertices and edges, consider this problem. Problem is find maximum independent set. So what do you mean by an independent set? Or actually not maximum. So find independent set. Yeah.
What an independent set is. Basically points which aren't connected.
Yes, I know Siddharth, you know that, but yeah, let me explain further. Independent set of size k. So what do you mean by an independent set? So you say that the points A and B are in an independent set if there is no edge in between. So let me name the points A, B, C, D. Right? So R, A, C, D. So is this an independent set, Tanish?
One second. CD. No, because CD is connected.
Exactly. So if you want to find the independent set, so there is an independent set which is ECB. So do you agree that this is an independent set?
Yes.
So does everyone agree that ACD is not an independent set and ECB is an independent set? Yeah. So yeah, once you have known this, so this is the problem. So I won't prove it to you, but the thing is that this has no efficient algorithm. So this has no algorithm which is efficient. But tell me, Tanish, so if I give you a graph, so basically if I give you this, and if I give you the set ACD, can you tell me a verifier which could efficiently give me whether this is an independent set or not? Or let's say, how did you say that this was not an independent set?
Because two of them are connected.
Exactly. So consider this verifier. So let's say you have ACD. So the verifier will first check if the number of hashtag elements is number of hashtag is the number of. So this is a notation is k. So because we want independent set of size k. So if it is k, if yes, then it will say, if it is not k, then it will output no directly. And if it is yes, it will say that choose any 2 points as Tanish did. So I think you all would have done this in Muralidharan sir's class. So you know that if you want to choose any 2 points out of the k points, it will be k choose 2 ways. And then once you choose a point, then you say, is there an edge? Is there an edge? If no, then you continue in this loop till it ends. And then once this loop is over, if you still get no, okay, so let me write this in a better way.
Okay, but I have a doubt. What is this thing right here?
What is what thing right here? Oh, that is number of elements. So we want an independent set of size k, right? So if the number of elements is not k, then you
Okay, so
reject it directly.
basically you run through A, B, C, and D, and basically, but what if it's not an independent set in the first place?
Yeah. So no. Firstly, we check if the number of elements is k. If it's not k, we reject. If it's a k element set, then we see if it's independent or not. So for that, what we do is we choose any 2 points which is not chosen, and once you choose the 2 points, then you see if there is an edge. Is an edge. Then now there can be 2 ways. If you see which is not chosen, so this is a loop. This loop will keep on running till how many times? K choose 2 times, because there are k points and you can choose 2 points. And if it gives no for all, if it gives yes for even one edge, so let's say, like for example, Tanish took the 2 points C and D, and he saw that there was actually an edge between C and D. So then he said that this is not an independent set. But if he can't find an edge for any 2 points, then he will output yes. So I think I went a bit fast with this algorithm. So does everyone understand this algorithm completely?
Yes, but like, then will we insert the values one by one? Because we need to find out how many there are. Like, so the verifier can't see, like, if the number we have inserted is correct. It can only see if the values you have inserted are correct.
Yeah. So what it will do is, so it will, so basically, let's say you have given the verifier A, C, and D, right? So what it will do is, it will, wait just a second, let me get this picture. Yeah, so what it will do is, and let's say your k is equal to 3. So it will see whether the number of elements in ACD is 3. It is 3, right? So if it was not 3, it will reject. Since it is 3, then what it will do, it will choose any 2 points. So let's say you choose A and C. Then it will say that if there is an edge, is there an edge between A and C? No. So since it is not, since there is not an edge, so it will go back. Then it will choose 2 more points, which is, let's say, C and D. So there is an edge between C and D. So once it gets a yes, it will output no. But if it gets no for all the things, then it will output yes. And now we know that this is efficient, because how many ways can you choose 2 points? Tanish, how many ways can you choose 2 points among the k points?
KC2.
Exactly, KC2. And we know that by definition, KC2 is nothing but k minus 1 upon 2, which is k square upon 2, which is polynomial, right? By our definition of polynomial.
Yes, thank you.
Yeah. So does everyone understand why this verifier runs in polynomial time? I mean, runs in k square time.
I know, but you said there is no algorithm.
Yeah, this is a verifier, right?
So there is a verifier, but there is no efficient algorithm, which means that this problem is not true.
No. So what I said was, there is no efficient algorithm that we know. So there could be algorithms, but we haven't found any. So that is basically this problem. So what this be,
Yeah, but then we'll have to wait. This is like it's like a time problem. We have to wait until we find something.
Exactly. So this is what the problem says. So there are a collection of problems which have a polynomial verifier. have a verifier,
Could I lift the leg from there?
but doesn't have.
Yeah, it's a verifier but does not have efficient algorithm.
Yes, efficient algo yet. Yet being the important word. Yes, Vagishan, what was your doubt?
Yes. So my thing is that let's say the function is doing if the amount of time is convergent, then it is definitely efficient. But then if it is n square time, then n square is diverging to infinity.
No, n square is still polynomial. So what you are saying by divergent convergent is when you have the summation symbol, right? And it's just n square, then it's still polynomial.
It is not at all summation, but when we graph y equals to x square, then it's very divergent.
No. So there is no like it's the
It's
thing
going,
is you
it's going
don't have your running
upward
time
instead
in
of going like this.
Okay. Can you please remove your annotation? I didn't that like divergent doesn't mean that, because if your running time t of n is summation n square, then this goes to infinity, right? This whole summation till infinity.
Yeah.
So that is what I meant by summation.
Oh,
Because for a fixed,
okay. And so we can do n square, but then n cannot be but you cannot do anything like 2 power n, so n should not or you cannot do n through and you cannot do n factorial or 2c n cannot be do, so the n cannot be r in ncr. So in the things where n is part of the operator, then only it's not efficient as a
yes,
polynomial.
exactly.
And the next thing I would want to say is if, let's say there is one algorithm. So let's say a point. It checks if it, let's say this is one. I'll rather just so let's say this is 1, 2, and this is 3. So and we are connecting, and these two are just connected. The 1 and 2, I mean 2 and 1 are connected, and 2 and 3 are also connected. Then if all are, if A and B are not connected and B and C are not connected, and so we are currently using the AND logic. So will logic be expressed in polynomial and
Yes, they take a constant number of times, so that doesn't affect our algorithm.
okay, and or not if and
Else,
if and only if and exclusive or and those kind of stuff. So they don't affect anything. Got my doubt.
yes. Yeah. So yeah, I guess we can. Yeah. Does anyone else have any doubts? Yeah. Okay. So let's continue. So
Sundar, is it okay if I just call out some name and just ask?
sure, sir. Sure.
Okay. So Manas, are you there?
Yes, sir.
Yes, Manas, have you understood what Sundar said, or is there any place where you need more clarity?
Sir, I understood.
Okay. Aditya? Aditya, can you unmute yourself? Okay. All right, you can go ahead, Sundar.
So 1 second. Could you give a brief explanation of this part again? I couldn't hear properly.
Which part? The last one.
Yes.
Yeah. Okay. So basically, what we showed is that we have a problem P. So if we have an algorithm A, which is efficient, then it implies that there exists a verifier V, which is also efficient. So we showed that, like for Sai and Tanish and others gave a nice proof for that, because your verifier can use this algorithm to see, diagrams, to see whether the solution is right or not. So this was discussed. So, but then Tanish asked, are there some problems for which the other side is still not true? So that's why we discussed the problem where we wanted to find the vertex cover of a graph and said that there is not an efficient algorithm yet, but we have an efficient verifier. So this is the whole problem, which is like the Millennium problem, first Millennium problem. So the first Millennium problem just says that if you have a verifier, then can you surely say that you will also have an efficient algorithm? So is this clear, or is there still something?
Yeah, I got the brief. Thank you.
Yeah. So yeah. So this is okay. This is good.
We have about 15 minutes.
Yes, sir. Yeah. So we'll complete this problem today, and then we'll start with the next problem in the next class, which is day after tomorrow. Yes, sir. Yeah, day after. Yeah.
Sure. Yeah.
So yeah, an answer to the P versus NP problem would determine whether the problems can be which can be verified in polynomial time can also be solved in polynomial, which is exactly what I said. So if you have a verifier, then you will definitely have an algorithm. But as I said, most people believe that P is not equal to N. So remember that we had shown that
Yeah, but
Vagishan,
P implies MP. It's a proof
yes,
one way. It's a one-way
exactly.
proof.
So,
We have profound implications.
Siddharth, can you stop annotating, please? Yeah. So as Siddharth and Vagishan are saying, we know that P implies HP. Oh, sorry, we don't know.
No, P implies
Sorry.
MP, but we don't know the opposite.
Yeah. So we know that if a problem P belongs to the class P, then it definitely belongs to the class NP, as Siddharth and Vagishan are saying. But if, and we also know that P not equal to, yes, Vinandan?
So I wanted to ask that if they have an algorithm for verifying the answer,
Yes.
why don't they just use the algorithm to find the algorithm to compute the answer in the first place?
So that's what I'm saying. That's so even though it seems like it should be obvious, the fact that once we have a verifier, it should be obvious that we should have an algorithm which will actually calculate the answer as well. But the fact is that it is very difficult. So if you just have the verifier, it is very difficult to construct the actual problem.
So the verifier uses a certain algorithm to find the answer, right?
No, the verifier is an algorithm which will tell you if the answer which you provided is a correct answer or not.
So it is not. So does it compute the answer to find cross check?
No, it might not always. So exactly. So in our proof, what we said that the verifier will directly use the algorithm, right? But it might not always do that. It might have some other ways of verifying it. Yeah.
Oh, so it's those other ways in which the direct computational algorithm is hard to find.
Yes. So direct computation might take exponential time, but the verification can take something like n square or some polynomial. So yeah, exactly. Very good point. So even though we showed that our verifier, so in this proof we showed that the verifier uses the algorithm, but this might not always be the case, and that is why this is a very hard problem. The p equal to. Yeah. So as I was continuing with, so since we know that p implies np and we know that p not equal to np, what does this say? So this says that there is a problem. There is a problem belonging to NP which has Devan, just a second, which has no efficient algorithm, right? Because we have assumed that we not. So yeah, Devansh, what were you saying?
No, sir, I erased it by mistake. Sorry.
Oh, yeah. So is this clear? Is what I have written here, is this point clear? So, Devan. Okay. So yeah, so I'll just repeat it once again. So if P is in, we know that if a problem is in P, then it is in NP. So if we know that all problems in NP are in P, then we are done. So, but if we assume that P not equal to NP, which most people believe, then there will be a problem in NP which can be verified efficiently, but which has no efficient answer. That is all I'm saying. So yeah, if it turned out that P not equal to NP, then there are problems in NP that are harder to compute than to verify. So yeah, so I guess, yeah, so the thing is, it is very, this has like tremendous application. So basically, if you like in a few years, I think you'll learn something which is called cryptography, or some of you might even be known to it. So cryptography has a very important algorithm. So this RSA algorithm is used, like widely used in cryptography even now. And this is based on the fact, so this works because they assume p equal not p not equal. So sir, yeah, we have 10 minutes, so I'll tell you what this is. So in this RSA algorithm, what they assume is if you have a number n, and if you want to factorize it into a times b, this seems like a very easy problem, right? But we don't have an efficient algorithm which will take a very big n, let's say a 15-digit number, and will factorize it into two 7-digit numbers. Since we don't have an efficient algorithm for this, the RSA algorithms and everything we have in cryptocurrency and all those stuff work. So if we can somehow show that P equal to NP, and we have an efficient algorithm for factorization, then the whole of crypto, like the whole security systems will crash. So yeah, they have a lot of applications in cryptography, in artificial intelligence. So in yesterday's session, you might have learned, like you might have seen what artificial intelligence is. So even a lot of algorithms in artificial intelligence work because they assume that P not equal to NP, and the reverse algorithm doesn't have an efficient solution. Yeah, then there is game theory. So so do you guys know the popular game Sudoku, which comes in newspapers and stuff?
Yeah, Sudoku. Yeah, I know that.
Sudoku is actually an NP problem, because if you have an n cross n grid with numbers, you can easily verify whether all rows have 1 to 9, all columns have 1 to 9. but a computer cannot solve Sudoku in efficiently. Like it will take a lot of time to solve Sudoku by itself. So yeah, so Sudoku is also an NP problem. Then you have economics. So a lot of models in economics. So the thing is, after internet and computers were all chess. So Devansh has asked chess. So chess is actually not even NP. So you can't even verify a solution in polynomial. So chess is actually one of the most complicated games. So game theory is a very wide field, and chess is one of the most complicated games in the class of game theory. So yeah, so chess is even higher than NP. So it's not even in NP. And then you have economics. So yeah, that was what I was saying. So because of all this computer and internet boom, so most of the economic models are now made on the computer, and so again it uses a lot of algorithms, and whenever there are algorithms, P equal to NP plays a very important role. So since this is such an important problem, it's one of the hardest problems of the Millennium. Yeah. Yeah, so I think we can end our session here, and next time we'll start with the perhaps the most famous problem of all time, the Riemann hypothesis. So if you guys have any doubts, you can raise your hand and ask.
Otherwise, like, should we stay back only?
What happened?
Like, after doubts are clarified, like now, like, should the ones without doubts stay back only?
Vinay sir.
No, I think you stay back until until the class is over. Yes, Sundar, you can take doubts.
Yeah. So Pragyan, yeah, you can.
Yes, sir. So who solved the Poincare conjecture?
So there was an Asian mathematician. I don't remember his name. So he solved the Poincare conjecture. And fun fact, he didn't even take the $1 million. So he just donated all the money. And he said that he wanted to solve the problem just for the beauty of it. He just did it because he loved math, and he just donated all the money that.
Okay, sir.
Yeah.
Sorry, Sundar. Maybe I missed the initial part when you said, did you tell about the prize money for the problem?
Yeah, I didn't. Yeah. So each of these millennium problems are like, if you solve them, then the Clay Mathematics Institute gives you $1 million. So yeah, that's
per
like
problem, right? Per problem.
Yeah, per problem. Yeah, so it's like 7 crore rupees if you can solve one of these problems. Yeah.
I don't know whether the screen froze or everybody is stunned.
Yeah. So Ishan, yeah, what was your doubt?
My doubt was that which of the means in the means Millennium Prize problem we are going to learn the most means compared to
Which of the following are we going to
learn the most means in
so
comparison.
the thing is, even understanding what the problem is a big task. So now whatever I have done in this 1 hour, I've just explained to you what the problem is, that too, like not even on a deep level, so just on the base level. So that is what I'll be trying to do even in the next class for the Riemann hypothesis. And the other 5 problems, if you ask me, even I don't know the problems completely. So the thing is, you will have to work for another 2-3 years the way you're doing. I mean, you are all very passionate, like, and you're very young, like you're 10 years or something. So if you give it 2 or 3 years, then you will be able to understand the problem. So this is just an overview. So you know about these problems. So once you learn the advanced concepts, you can revisit this problem, and maybe hopefully some of you will be able to prove it in the future. Yeah. So these are the 2 problems. So we'll just discuss today. We discussed about the PNP problem, and on 13th we'll discuss about the Riemann hypothesis.
Yeah, but are you telling this the truth? You mean no one has solved the P versus NP problem so far at all?
Yes, I am telling the truth. Like,
Yeah, but
I mean,
but how many of the 7 millennium problems have been solved?
only
Only
one.
one.
Yeah,
So you're saying that if I solve it, I'll get $1 billion.
$1 million. But yeah,
I'm dedicating my entire life to this.
Yeah,
Just,
I'm
that
also
is
just
going
for
to
the
that
give
is
money
money?
what
and I'll ask
professors have been
Yes,
doing.
for the money.
Just for
I'll
the
buy a
I'll
money?
be
lot of
able to buy
roses
so
too.
much jelly with it.
Just
I'll
for
buy a
the
lot
money?
I'll
of
be able to
I
get a dog.
kind of won't do it just because for the money. I'll do it
I'm
like
doing it
that
for money and
person
the
who
fame,
rejected
okay?
the dollars.
I'm
I'll
doing
be
it for
like that
money and the
person
fame.
who rejected the $1 million.
No,
But
no, Siddharth, you accept it and you give it to me. I'll be happy with it.
the thing is,
You
Sasha,
don't have to reject it.
this might be one of the hardest ways to earn $1 million. So the first time someone said this, like introduced these problems to me, they said that this would be one of the hardest ways to earn $1 million. Like, yeah,
I heard it is $1 billion. That's why I got so. I'll eat a tomato
excited.
for it. I won't eat a tomato for $1 million.
Yeah, but I won't take it. What I shall do is immediately when I solve the problem, I'll just reject the $1 million.
Yeah, that is what. Wait, what was his name? Grigory Perelman. Yeah, that is what Grigory Perelman did. So in 2006.
Yeah, I'll be like him rejecting all that money. Yeah, I'll reject it.
Yeah. Okay. So anyone else has any doubts, queries, like anything?
Everyone
Yes,
else
I had
can accept.
read it in the camp reading material. It was written that these are essential to complete to follow Dr. Hariharan's class and lectures on Raymond's hypothesis.
Yeah, yeah. So that was the Riemann zeta function, right?
Yes.
Yeah. So we will use that. We will see how it connects to the
Asha, you're going to
millennium
organize a bank.
what?
Nothing. Just usual Siddharth.
Okay. Yeah. So anyone else wants to ask anything, or yeah, it's 12:45.
I hope Euler rose from wherever he was there, and he died and he got revived and he solved the problems.
I think it would be a better idea to rob a bank because there you can get more than $1 million.
I think
Faster.
we should stick to this. Yeah, I know that
I would rather
money
stick
has
to
no
this
bank
and
robberies. I get it.
I will try to like buy
You brought up
like
that point.
something.
Before you can even rob.
okay. Sundar, I've put everybody on mute. You can unmute yourself. Right. Sorry, Sundar, you were saying something. Sundar, you'll have to unmute.
Nothing, sir.
Yeah.
Hello.
Yeah.
Yeah. So yeah, if anyone, like, if no one has any doubts, we can conclude this.
Yes. Okay. Pranali, are you there? Pranali? Okay, Sundar. Thank you so much. I remember the first time we both learned about this P versus NP problem, in Rajiv sir's class about, I think, 5 years ago. And I can recollect how lost I was, when this was introduced. And it took a lot of time for me to get a basic understanding. Even now, I get confused many a times when I think about this. You feel that you got it, but then after some time you feel that no, maybe there is some confusion. So I'm just saying this for the sake of everybody, in case you feel that, oh my God, this was a little hard and I did not get 100% out of it. Don't worry. Like Sundar said, these are something like the most challenging problems of the millennium, and this is the simplest one to understand. So we can imagine what would be the kind of complexity for the other ones. So don't feel intimidated. And I think, Sundar, you couldn't have put it in simpler ways of explaining such a hard problem to these guys. I think you did an amazing job in terms of bringing it down to everybody's understanding. So thank you so much, Sundar, for this wonderful presentation, and we really look forward to your